Okay, so let me just spend maybe 10-15 minutes, not so much on computer vision, because that's been one area where there's been a lot of success, and I just wanted to show you what's happening in this area, particularly with respect to deep net. So here's a simple example, very well studied example, object recognition, right? Given an input image, you try to identify object that it contains. Challenging problem, typically it's a classification problem. And these convolutional neural networks, you've probably heard about, those are kind of the state-of-the-art systems right now. So you take an image, you have convolutional, you have pooling, sometimes it's a normalization, you go through the densely connected layer, and then you make a prediction. So it's a specific architecture. And if you think about the convolution, you have an input image, you take a little patch and you just convolve it, right? Running it across the entire image. That creates something called convolutional map, and then you do pooling, which is take a subset of a 2x2 or 3x3 and pick the maximum. So it's just to get a little translation invariance, and then so it's a pooling operation, and then you create multiple maps, and that would be one layer of a convolutional network. Right? So it's just a specific architecture that people are employing. They have multiple layers of those and such. Yes.
Is pooling still very commonly used, or is a convolution to convolution more common?
Yeah, so now people are using convolution over convolution. They're using network and network. Sort of, there are different pieces, but pooling is still used in these models. And just to show you some examples, people use it on optical character recognition, street traffic signs. You can do pedestrian detection, try to identify people in images, and again, you can obviously see why these kinds of problems would be very important, particularly in the space of all the excitement that's happening in the industry today. Like, if object detection, another piece, there's a lot of work, and these systems do work quite well. There's an ImageNet data set, and actually, just to show you, it's one of the standard benchmark data sets that people are benchmarking the systems. These are the examples of a hammer, right? So you can see that it's a pretty difficult data set. It's not, this is just a particular class, a hammer, that you're trying to classify. And there was an important breakthrough that I want to point out. Back in 2012, there was a paper coming of Jeff Hinton's group, the well-known AlexNet. If you've heard about this particular model, was built by Alex Krzyzewski, Ilya Sutskever, and they've basically built a system that had 7 or 8 convolutional layers, a fully connected layer, and an output. And back in 2012, on 1.2 million images, they basically halved the error of the best systems out there. And that was kind of exciting, because a lot of people felt that wasn't a valid result, but then later on, it actually turns out to be quite an impressive result. So these are some examples of what you can classify. It's a leopard, jaguar, so classifying it leopard. And then you have these kinds of images. If you look at that image, the model would basically predict it's Dalmatian, but the correct class is cherry, right? So you see there's a lot of noise in these kinds of images. And that happened in 2012, and that basically moved the computer vision field, started to pursue these kinds of models. Now, the architecture, how can you secularize architecture? So this now, again, comes to the problem of how do you select, and most of the time you're just doing manual tuning of depth, width, parameter count. So how to choose the architecture, those are the hyperparameters, number of layers. Typically people use cross-validation, grid search, one way of doing it. So in a lot of applications, you have lots of GPUs. You can afford doing random search, grid search. There's a little bit smarter strategies and perhaps new ones that are coming up. There's a work on Bayesian optimization, but that still is quite an open problem. How do you search hyperparameters? That's generally, it's a hard problem. So people who have intuitions as to how to build these models, companies would pay a lot of money for people who can do that efficiently, basically. So here's AlexNet. You basically have 8 layers. It was trained on ImageNet. It achieves 18% error, top 5 error on the ImageNet dataset. And there was some work coming from Rob Fergus at NYU's group where they basically said, well, what if you just remove one fully connected layer? So you basically remove 16 million parameters from the model. The entire model has about 50 million parameters. So you're only losing 1% drop in performance. So maybe that wasn't that important, right? What if you drop some of the convolutional layers, right, and just train this model? And there's a big drop in performance. So people started analyzing, is the depth really matter? And some of the conclusions were the depth actually matters a lot, at least for these applications, for the computer vision. And so it's sort of the whole field since 2012 was kind of an interesting evolution. It's 8 layers, and people thought 8 layers is way too many layers. Then there was a paper coming from Google where they've built 24-layer model, and it achieved really good results. So you have these systems, there's a convolution, there is a pooling, there is something that's called inception module, which basically was combining pooling at multiple levels. So it's like 3x3, 5x5, 1x1. It was just basically very careful search for the architecture. And it was doing really well. You have lots of different things. They basically removed convolutional, they removed the fully connected layer, and they've reduced the number of parameters to 5 million, right? So that kind of shows you that the original AlexNet model had 50 million, or about 50 million, now we reduced it to 5 million. And that was a better model, better performing model. So 10 times as less parameters, much deeper, with different convolutions, specific architecture, and then we're doing 6.7% on that particular ImageNet. Now, the interesting thing about these models is that one question you might ask, well, who cares about this data set? Like, does it actually give us something? And one interesting thing about these kinds of models is that people have shown that if you take features, so if you take these representations from these models and use them for other tasks, like caption generation that I've shown you, or for detecting other things, it turns out that these features are actually quite useful in terms of transferring to other different tasks. So, in a lot of different domains, if you're trying to solve something new, the first thing people would do is they would take these features and use them as initialization for solving. So it seems like these features are very transferable across different data sets, which is quite important.
Do you just hardwire those features, or do you try to?
A lot of times you just hardwire. A lot of times people would just hardwire and then just based on that. So it's like instead of using SIFT, you use what they call conv5 or conv7 features, or sometimes you do backpropagate, sometimes you do adjust. There are some examples where they do adjust, but in some cases those are reasonable features to use as well.
What if your dimension of the image doesn't fit the input map?
Good point. It's fine. The reason why is because you're using convolutions. So if your image is bigger or smaller, that basically means that these feature maps will become bigger and smaller. So your output is just going to be a little bit bigger. But in the end, you're just averaging all those maps as well. So these systems can be applied for big images, small images, and so forth. So it's quite flexible. Yeah.
Do we know how the measurements on ImageNet translate to these other applications when these features are used?
In many cases, so for example, it does translate a lot. If people are using these models for this something called Pascal data sets where you're detecting cows and like objects, other kinds of objects, and they do translate.
So if you get a 5% improvement on ImageNet, does that mean you should expect?
Oh yeah, absolutely. Absolutely. Like, if you read like some of the vision papers, the typical comment you get back is that, why are you using AlexNet? You should be using GoogleNet, right? Or what the results would look like on GoogleNet, because you basically, if you just substitute one features for another, your models will perform better. That's just in general for, not for all data sets probably, but for a lot of data sets. If you replace with a better model, performance goes up. It's just an empirical observation, right? Yes?
What's the difference between a convolutional layer and the units that you described before, where you apply?
So the previous in the standard is just the only difference is that what I was describing before. Typically, these would be fully connected models, right? So basically, every single neuron or every single unit is looking at the entire input. In convolutional models, every single unit is looking only at the patch, right? And you just doing parameter sharing. You sort of doing convolution across the entire image. So it's a parameter sharing, and it reduces the number of parameters that you need to run.
So the units are the same, but the
units are the same, right? Yeah. And then, so just last year, there was a paper coming from Microsoft, so it's called Residual Networks, and these models basically have 151 layers. So people are just designing, and they work much better. And there is an interesting trick that was introduced, which is the skip connections. So the idea here is that whenever you train these very, very deep systems, sometimes optimization can be very hard in general, because you have 151 layers, it's just very hard to train. So they just introduced these skip connections so that information can propagate. If this is the input, this is just the identity, and this is nonlinearity, right? So it's sort of, you have these skip connections plus nonlinearity. So if the information needs to propagate, you just propagate forward. And these are kind of the systems that people are building right now, right? So there is a lot of kind of interest in the community where people are just, why do you need 152 layers? Well, and yes.
Can you also use these features?
Yes,
Plugin.
plugin, that's right. So I would recommend, if you're trying to solve some kind of vision problem, you take these features as an input. These are just better features. And now Google has come up with its own version that's kind of comparable to these features and such. So a lot of the time, choosing the architecture is task dependent. So as I mentioned, again, it's just searching for the number of parameters, number of convolutions, and so forth. So let me just finish here. So this is for the supervised learning. So this is state of the art on the supervised learning land. So let me, yes.
So does the success precision on ImageNet predict accuracy in the other tasks? That if you take the features, better accuracy on ImageNet would also be better for
Other tasks.
things that you plug in?
Yes, so generally, for example, anytime you're working with images, so I can give you an example, which is again, was very surprising. ImageNet contains 50 different kinds of mushrooms, right? 50 different kinds of different dog breeds, right? And you're training on these 1,000 classes, and then you take those features and you want to build, I don't know, detecting people, or getting a caption model that mostly talks about what people are doing, whereas people are not really a class on the ImageNet. And it turns out these features are quite useful. It somehow represents a person as a combination of a weird kind of a mushroom and weird kind of a dog breed, right? Effectively, it takes these features and basically says these features are useful for detecting and representing people. So there is a lot of interesting transferability happening there. So it seems like if you're trying to solve a multi-way classification problem, you're trying to classify 1,000 different classes, you will inherently learn features that could be generalized to other classes. So there's a lot of kind of work in that space. People are trying to figure out exactly what these models are doing.
I think I've even seen crazy things like you can transfer looking at X-rays of cancer patients or some such crazy thing.
Yeah.
Completely different.
Completely different, right? And that's so it does extract some invariance, right? It's sort of like it extracts edges, it extracts certain things, and yeah. Initially, you would have thought that it's completely irrelevant, but because it's such a diversity, you're trying to you solve all these 1,000 different classes. It tends to extract features that are useful for lots and lots of other things.
Like there is no overfitting. The Microsoft Net, does it do better?
Yeah, Microsoft Net would do better. Like just generally on average, sometimes there's, you look at the paper and you say, oh, my model does better. And then the question, well, did you use ImageNet features? Or sorry, did you use AlexNet features? Or did you use ResNet features? Well, for my problem, I use ResNet features, but for competitor problem, I use AlexNet features. And of course, your method is going to be better just because, yeah, it's interesting. The field of computer vision is an interesting field right now because a lot of it is now based on the architecture, design, and such.
Can you somehow gauge the degree of overfitting?
What do you mean by gauge the degree of overfitting?
Well, you said before that if you just run it without any penalization, you'll get 0,
Right.
and then you add some sort of penalization, so you
Right.
presumably will decrease overfitting from that.
Yes, that's right.
But something must still be left, right, in this result.
Sure. There must be, yeah, absolutely. But I don't know. I mean, it's very much task dependent and problem dependent, right? What you're trying to solve. Okay, so let me actually switch a little bit of gears and start looking at unsupervised learning or learning generative models for the rest of the tutorial. And we've looked at supervised learning. In unsupervised learning, there are sort of a few different classes of models that I'd like to talk about. There are non-probabilistic models, like sparse coding models, autoencoders, that I'll say a few words about. And then there are probabilistic models. And in probabilistic models, there are tractable models. And more recently, these models have been showing some really good results. These are fully observed belief networks. There's something called neural autoregressive density estimator. And then there are a few models like pixel RNNs based on recurrent networks for modeling distributions over the inputs. There are non-tractable models. A lot of them are based on graphical models, Markov random fields, and Helmholtz machines and variational autoencoders. These are recent models that people are exploring today. And all of these models are trying to explicitly model the density, some density over the input space. So you have to specify what that is. And then there are classes of models like generative adversarial networks or moment matching networks that basically modeling implicitly the density. So they don't really specify what the density is. So these are interesting kinds of models because these are not based on maximum likelihood estimation, but recently they've been showing real success. A lot of people are looking at these models. Most of them are set up in sort of game theoretic viewpoint. Okay, so let me look at just quickly over the basic building blocks. These are non-probabilistic models. Probably most of you are familiar with these models, but I would still like to just point a few because these are older models. They've been around for a long time, but they'll form the basis for these more complex models. So let me just quickly say a few words about sparse coding. How many of you heard about sparse coding models? Okay, so most of you. So it's a beautiful algorithm, and the objective is, given a set of input data vectors, you want to learn a dictionary of bases. Right? So you want to say, I want to represent my input as a linear combination of the bases. And I want my activations, I want my the linear combination, these parameters to be mostly 0. Right? So you're basically saying each data vector is represented as a sparse linear combination of the bases. And then it turns out for images, you tend to learn these representations, right? So you're basically saying every single patch is represented by some linear combination, sparse linear combination of these bases. And these models learn quite useful bases, at least in images and text and such. So, and then you take these representations, you can think of them as just using them as feature representation, right? Which bases occur in a particular patch. The training, it's a well-defined training problem. You have input patches, you learn a dictionary of bases. There is something that's called reconstruction error, so you're trying to reconstruct back the original input. It's a sparse linear combination of the bases, and you have a sparsity penalty, and that's typically L1 sparsity. And you perform an alternating optimization problem, you fix the basis, you solve for activation, which is a standard lasso problem. Or you fix the activations and you optimize for the dictionary basis, which is a convex quadratic programming problem. So you can sort of do alternating optimization and you can solve this problem. And at the test time, I give you a new image patch as well as the learned basis. You want to output the representation. And again, this is just a standard lasso problem, right? And you can have that representation. Very simple, these kinds of models are used a lot by neuroscientists, and they do give very good results. So here's just some example on classification. You can just, if you take a convolution of these learned bases, and you apply this particular feature, across the entire image, you get this representation. So for these different features, you get these representations. You can think of them as coefficients, and then if you classify them as a support vector machine, just as an input, you can do quite well, right? And this is something that was done back in 2007 by Stanford, group at Stanford. This is one of the core algorithms that people do use. Now, if you think about interpreting sparse coding, the way to interpret sparse coding is that you have sparse features, and you have explicit linear decoding back into the input, right? It's just a linear combination. You have sparse features in encoding. But if you think about, given the input, how do you find these activations? You can think of it as an implicit nonlinear encoding, right? Because you're solving an optimization problem to find these activations. You have to solve lasso. So the reconstruction is linear, explicit. The encoding is implicit and nonlinear function of the input. And that brings to this whole idea of autoencoders that people were trying to explore also. And it's, again, it's a very old idea. It dates back to early 80s. You have an input, you encoding, get some feature representation, you decode it. Right? And this is, you can think of this as a feed-forward bottom-up encoder. Oops, sorry. And hold on. Oops.
So, Russ, could I interject one comment?
Sure.
So, from a theorist viewpoint, I mean, this used to confuse me in the beginning, so I wanted to mention
Sure.
that if you think of it as like coding theory, which is where encoder decoder comes from, the names are flipped, right? Because you would think of the feature representation as the hidden thing, and the image as a received message.
Yeah, sure.
This used to always confuse me.
I see. Right. Because in our field, we can think always input is an input, and the encoder is the way of getting to the features, and the decoder is going from the features back to the original input. Yeah, that's true.
So it's not
For the
encoding, decoding in the error correcting code sense, but in this feature learning sense.
Right. That's right. That's a good point. And then the detail what goes inside both of these encoder-decoder is really matter, right? Because you need some constraints to avoid learning the identity, in principle, all right? Because if this is just an identity and this is identity, then it's useless. And so there's a lot of, you can use sigmoid nonlinearities to get binary features. If you're interested in getting binary features, if your input has some Gaussian distribution, then you have a linear function, linear decoding, or if you have binary input, you can have sigmoids on both, and that sort of relates to something called Boltzmann machines that I'll talk about later. And again, this is the autoencoder, just as a reminder what that is. Again, in this case, it's a standard neural net, one-layer neural net. You encode, you decode, and then there's a loss function, so you're optimizing these loss functions, right? This is what we've seen that before. Now, one point I want to make is if both the hidden and output layers are linear, then you're essentially recovering PCA. So that's if you're looking at the squared error. That's right. So if it's a linear and you're looking at the squared error, squared reconstruction error, you're recovering PCA. So sometimes people think about autoencoders as a nonlinear extension of PCA. Now, there is one idea that was developed, I guess, back in 2008, and a few people also looked at this idea of denoising autoencoders, which is, it predates dropouts, but the idea is that what you want to do is you want to randomly assign a subset of the inputs to 0 with some probability. Or maybe sometimes you want to just use, you want to corrupt the input with some Gaussian noise. So there's a process where you get some input, you have some noise process, you're corrupting the input, and then you're reconstructing back the original input. So from noisy inputs, you're reconstructing back the original input. And the reconstruction is computed from the corrupted input, right? So these kinds of models have shown to sort of give interesting results. So it's almost like you can think of it as a manifold of digits. Right? You're taking the input, you're corrupting it, and then you're trying to get back to the manifold of the images. And it turns out, it does give reasonable results. This is just one example where people started exploring. So if you look at the features, if I look back between these two features, you tend to find slightly better representation. And again, what does it mean to have better representation is not clear, but sometimes you sort of get stronger edges, and you do get better results if you take these representations and you classify that. There's been also some work on something called predictive sparse decomposition, where the idea is you're trying to solve sparse coding problem. This is a sparse coding problem, right? But then you also have another term which basically tries to find the right encoding for the latent representation. Right? So it's almost like this term is basically saying that I want to find what the right representation should be, so that's my encoder, and that's my decoder. Right? So it's almost, sometimes can be viewed as in a sparse coding, you have to solve lasso. But maybe you can use an encoder to almost guess what the solution of lasso should be. Right? And if you can guess it fairly well, then maybe you can use that instead. So that's kind of just for fast inference at test time. So people started doing that, and then obviously these ideas of, okay, can we stack these things together, right? Okay, we can stack these things together, we can add the classifier, and then this is sort of greedy layer-wise learning, and then you can remove the decoder and just say, okay, I'm going to be using my model to classify things. And the actual question was, why do people do this? Is there kind of a theoretical justification? Is this, or is this just a pure practical hack? And I'll try to answer that question through the tutorial. And people are using standard convolution and so forth. So back in 2008, 2009, that was sort of the state of the art, to pre-train it, and then people use stacked autoencoders, and they do work reasonably well. And people started looking at, this is autoencoding. You know, here's an example of, you pre-train the stack of, I mean, these are restricted Boltz machines, but you can also pre-train them using autoencoders. But you pre-train these models, you unroll, you go to some bottleneck layer, you reconstruct, and then you fine-tune the whole system. And it does reasonably well, right? Here's the face, and this is the output of the face. So you can compress these 28 by 28 images into 30-dimensional representation. Here's just some examples. This is the original input. This is what the reconstructions from 30-dimensional autoencoder, and this is what PCA gives you. Right, so you can sort of see that PCA is, you know, just a linear version. It kind of, a lot of these things look like snowmen, right? But it's interesting. It sort of has these interesting regularities, right? It removes glasses, so you can see that glasses disappear because that's one piece that the model doesn't preserve. Or it removes mustaches, because I think there was only one person with a mustache, and so it's just basically not worth to keep that information in the 30-dimensional code. And this is just another example that I've shown you. Initially, if you use these kinds of models, you can find low-dimensional space, primarily for visualization and also for retrieval. And this is a model latent semantic analysis, but this is based, you can think of it as a PCA solution. It's a linear projection. So it does preserve some class structure, but it doesn't preserve, the nonlinear model does preserve a lot more structure. There's another class of models that I wanted to point out just briefly, which is this idea of, because you're working with binary codes, what you can do is you can encode your input, let's say a document or an image, into a binary space. And it turns out searching in the binary space is a much easier problem. You can search through, and there's been a few papers that show that you can search through billions of documents or billions of images, basically a fraction of a second. So having specific binary representation, binary encoding is quite useful. There's been a lot of work in the vision where you have an image and you just look at the binary representation. You do nearest neighbor search in the binary space. So it's an interesting also optimization problem. How do you go from images to the binary, and can you actually optimize for the binary codes? I think it still is an open problem. Okay, so let me now jump into the other classes of models, because I think these are also quite interesting classes of models. So let me talk a little bit about Boltzmann machines, and a class of models called restricted Boltzmann machines. This is an example. Before I show you what these models are, this is an example of a generative model. It's a Boltzmann machine model, has multiple layers, and you're trying to model the distribution over these characters. Right, so you have Arabic, you have Cyrillic, you have Sanskrit, and you can ask the model to say, can you generate me images of Sanskrit? Let's see if that actually works. So what this is showing is it's basically showing a system where hidden variables, these are binary variables, so they're on or off. And as you're running this model, and I'll explain later what the model is actually doing, it's basically a Markov chain Monte Carlo simulation, and as it goes through different states, it generates different Sanskrit characters, right? So you can see that this space, the input space, is fairly complicated because there's lots of different characters, lots of different things that are happening. And the question is, can you actually model what the space should look like? You can also do pattern completion. So this is another way of, because these are modeling probabilities of the input space, you can sample from given half of the image what the other half should look like. And you can see it can sort of go through the space of different different characters consistent with that representation. So you always condition on that representation. So it does reasonably well. And why this is so difficult in general, whenever you're doing unsupervised learning, you have to kind of solve this problem, which is you have 28 by 28. It's 28 by 28 image. It's a very simple image, in fact. But there are 2 to the 784 possible images. Right? So that space is exponential. So how do you deal with that exponential space? Obviously, there has to be some approximations. So let me point out there is a class of models, fully observed models. So what you do is you basically model conditional probabilities. You can basically say, you have to define the ordering, but you can say if I'm modeling 784 pixels, I'm going to pick the first pixel, sample it from some probability, and then pick the second pixel given the value of the first pixel, and so forth. So you're basically modeling the product of these conditional probabilities. And each conditional probability can be a complicated neural network. And that was a little bit surprising, even to me, that there's been a number of successful models. People are pushing by saying, I'm going to predict this pixel given the previous pixels, and I'm going to use a multi-layered deep neural network to really predict precisely what the value of that pixel is. And this is what the sampled images look like, which is really impressive, right? By just modeling these conditional probabilities. The only problem with these kinds of models is that it's not clear right now what are the representations, are there latent representations that these models are using, right? So for example, if I want to classify what's happening in those images, how do I take what these representations are? Because these are all just conditional modeling, one pixel given the previous pixel, next pixel given the previous pixels, and such. But it's still like people in 2016, last year basically pushed these models, and they can generate pretty impressive.
Do they use a different neural net completely separately trained for each pixel?
For each pixel, yeah, that's right. I mean, they share some parameters, but to predict one pixel based on 20 pixels that you've already predicted, that's a big multi-layer neural net that basically predicts the value of this pixel, right? So it can be very precise about what you want to put in there. And they use convolutions, so they look at the neighborhood of what you're trying to predict and such. And it's pretty impressive what they can generate, actually. It's a little bit surprising that by doing that, you can actually generate realistic-looking images.
Is there any order to how they do the pixels? Is it just an obvious order?
Top to bottom, I guess. I mean, you can play with a lot of different things, but most important, you start at the top, and then you're looking at the neighborhood to generate the next one. So you try to maintain some consistency in what you're generating. But let me talk a little bit about a different class of models. These are graphical models, Markov random fields. And there's one particular model called Boltzmann machine. You can think of this model having stochastic binary visible variables v and stochastic binary hidden variables h. Right? So you can think of these variables as representing pixels in an image. And you can think of these hidden variables as representing features that you see in the images. But what I can do is I can specify the joint probability distribution over the visible and hidden variables. Right? So this is nothing more than a Markov random field with pairwise potentials. Right? And you have these unary just the biases in the system. So for those of you who work with Ising models, for example, this is nothing more than an Ising model, but that has a bipart type architecture. And what's interesting thing about these models existed since I think they were developed by Smolensky back in '86. What's interesting about these models is that I can look at this conditional probability. I can say conditional on the hidden variables. I actually have an explicit definition of the conditional probability over the input. It's just a product of logistic functions. All right? So what that means is that if I tell you the features, I can generate the image. I can sample the image. And then if you take this particular model and you learn on these handwritten characters, this is what the features look like. So a lot of them do look a lot like what you get out of sparse coding model. Somewhat similar, and given a new image, you're basically saying, well, I'm going to be representing it some combination of these features. And most of the time you get sparse representations, not quite sparse. I should be very careful what I say here. These are not zeros, but most of them are close to zero. You can make them be sparse. So it's kind of similar to what the sparse coding model does. But the interesting thing about this model is that I'm going to show you later is that inference in this model basically is exact. Given the input, I can tell you what features I see in the data. Yes?
Some regularization here, or is this?
So what I do?
And how do you get sparse representations? Do you regularize or is it natural from the probabilistic model?
So in many cases, you do actually have to regularize. You have to enforce the sparsity constraint. Yeah. But how do you do training with these models? Given the data, you have the proper probability distribution. You can maximize the log likelihood objective, standard. I can take derivative of the log likelihood with respect to parameters. There is a little bit of math, but it comes down to what's important. It comes down to being difference between two terms. And sometimes these are called expected sufficient statistics driven by the data, and these expected sufficient statistics driven by the model. This is just standard. If you think about this model, it's a log linear model. You're just matching sufficient statistics. And it turns out that for this model, this term is easy to compute because you have this specific bipartite architecture. So you can compute, you can do inference, there's exact inference in this model. Given the data, you can infer the distribution of the hidden variables exactly. This term is difficult to compute, right? This term requires exponential, it's exponential in many configurations. You have to, if you wanted to compute it exactly, right? Remember this 28 by 28 image. If I want to, compute the expectation sufficient statistics, I would actually have to enumerate over all possible images. Most of them would have close to zero probability, but nonetheless, this term is difficult to compute, and that comes from the derivative of the log of the partition function, normalizing constant. So this is something that's pretty standard for pretty much all undirected graphical models. So what can you do? Well, this is easy to compute. This is difficult to compute. And typically, people use MCMC methods, kind of Markov chain Monte Carlo methods to approximate these expectations. There's been a lot of work people are using. If you're familiar with variational inference, there are approximations based on beta approximation and so forth. And you can also use some of the variational techniques. But generally, for these kinds of models, Markov chain Monte Carlo works much better. So let me show you just quickly how do we approximate this exponential sum. And the way to do it would be to initialize with some configuration. You sample hidden variables from the conditional probability, which you can compute exactly, and you just run Gibbs sampler. You sample visible, you sample hiddens, and so forth. Right? And the approximate maximum likelihood learning here for these kinds of models, you start at the data. For example, you could start at some random configuration. You infer the hiddens, you infer the visibles, and so forth. So you're running this chain up to infinity. Right? When you run it up to infinity, you'll reach equilibrium distribution just because you're running a Gibbs chain. And you can take those samples and get an unbiased estimate of the expectations. Now, there is one algorithm that was due to Jeff Hinton back in 2002, which basically said the following. Instead of running this thing to infinity, just run it one time. And this is something that's called contrastive divergence. It's a biased algorithm, but you basically update the hiddens, you update the visibles, and you just do it one time, and then you approximate these expectations by just samples generated from reconstructed data. And it has a very good intuition. It's basically saying that if I start at the data and I slightly perturb the data, my learning algorithm basically should say, don't perturb data as much. Right? So the proper way of doing it would be to run a chain up to infinity to figure out what the distribution is, but this is almost like a local algorithm. So it kind of shapes around the data point, makes them more probable, around the data point, just carves, lowers the probability. So it's the algorithm that almost like an autoencoder. In some cases, the autoencoder would say, given the data, infer the hiddens, reconstruct, and make sure that these are the same. In contrastive divergence, you're basically saying, make sure that the distributions here are more or less the same. And you can apply these algorithms to other kinds of data. So you can model real valued data. You can say your stochastic, if your visible variables are stochastic. In fact, there is a generalization to other members within exponential family models. So you can build these hybrid models where your hiddens can be binary, your visibles can be real valued, they can be count data, or you can have gamma distributions and so forth. depending on what kind of problem you are solving. So here, if you apply this model on these images, you get these features, right? Again, a lot of them do look like features you'd get from sparse coding model. And again, the intuition here is that given an input, just have a linear combination of those to represent your input. You can also apply this model to modeling count data. So in this case, the conditional probability here is just given by something called softmax, which just gives you the distribution of a possible words that you see in a document. Again, details are probably not that important, but what's interesting is that, you know, if you use it on the documents, you tend to find some versions of topics. Right? So here, if you apply it on vision applications, you sort of get some features. If you apply it on text data, you have to twinkle a little bit with sparsity here. You can discover reasonable topics. You can also look at one-step reconstruction, what these systems are doing. Right? Notice one thing, unlike an autoencoders, my hidden space can be of much higher dimensionality compared to my input space. Right? Of course, I can overfit, but in general, these systems will not learn the identity function. They don't have an incentive to learn the identity function. Here's what, you know, just some examples. If you give it chocolate cake as an input, you infer the states of the hidden variables, and then you look at the reconstructions. You sort of reconstruct back the input. This is what the system would reconstruct, right? It says chocolate cake, sweets, desserts, cupcakes, flower, and then there's the Japanese signs, flower, Japanese sign, Japan, Sakura, and so it tends to capture some of the dependencies that you see in the data, right? So if I give a chocolate cake, the representation that I'm learning is a first hidden representation of Boltzmann machine, effectively modeling all of this. Some representation there. You can also use it for collaborative filtering. It's just another application where you have inputs, which is a multinomial visibles over the user ratings, and you have binary hidden representation, which is your user features. And it does find interesting things like genre. So if you take a particular hidden variable and you look at the strongest connections to these movies, which effectively, you know, these are ratings for different movies, you tend to find some notion of genre for these models. In fact, the interesting thing, we found that there is one hidden unit dedicated to Michael Moore's movies. So that basically shows that some people really like his movies or hate his movies. There is a very strong piece there. So you can model different kinds of data modalities, but the important thing is that you can infer the states of the hidden variables exactly, right? So this is unlike in a lot of Bayesian models, right, where your inference is expensive. You have to figure out what the posterior is. Here, just by definition of the model, given the input, I can quickly tell you what the distribution of the topics or what's the distribution of the features that you see in the data. And in many practical applications, that turns out to be quite important, just because you want to make sure your inference is fast. There is another intuition that I want to convey here. Is these models are sometimes called product models. So if you look at the literature in the late 90s, early 2000s, sometimes these models are called product models. And the reason why is here you have a joint distribution. The joint distribution is over the visible and these hidden variables. It's a log linear model, right? If I take the log of the probability, it's linear in the parameters. But if I marginalize out, if I sum out the states of the hidden variables, I have this funny thing, which is the product of a bunch of functions. So what's happening here? Let me give you an intuition. Suppose I'm finding these topics in the data. And I say that I'm seeing topics government, corruption, and mafia. If I'm seeing government, corruption, and mafia, the word Silvio Berlusconi will have very high probability, right? You know who Silvio Berlusconi is. Right, so that's so what does it do? That's a product model, which basically says that I have each topic define some distribution of a word. So there's some distribution over the input space. And what I'm doing is I'm multiplying a bunch of these functions, by a bunch of these distributions and renormalizing them, right? So this has the effect that my distribution here could be very precise. It could be very spiky. And that's very different from mixture-based models, right? Or if you worked with topic models like latent Dirichlet allocation models, in those models or admixture models, you typically choose a component and then you generate a word or you generate a particular instance from that component, right? Here you're really taking intersection of a bunch of distributions. You're modeling one very spiky distribution. So if I tell you what topics I see in the data, what features I see in the image, I can be very precise about what I'm going to be generating, right? And it turns out, these kinds of models work a little bit better for retrieval in particular. Okay, so let me just talk about deep belief networks. Sorry, it should be deep belief networks. So I wanted to quickly say a few words about these kinds of models. These are older models, but they were developed back in 2005. And I think that these kinds of models basically gave rise to a lot of deep learning kind of models, because it was one of the first algorithms that basically shows that you can have a generative model, but there is a fast, greedy layer-wise pre-training algorithm, and there was a very good justification for the algorithm. So, and there was a way of inferring the states of the hidden variables that can be done very easily. If you're trying to infer the distribution of the hidden variables, you can do it. There is a fast approximate algorithm for doing that. Now, the model itself was a very weird model. It's a hybrid model, which is an undirected graphical model sitting on top, followed by a directed model going all the way down. And that was because of a specific training procedure. These models have this particular structure. So it's really a hybrid model between directed and undirected graphs. So deep belief network, the way to think about this is to say, well, if I learn this model, I can find these little edges. Or if I use it on text, I can find some notion of topics. But maybe if I add another layer, maybe I can start capturing some internal representations that can capture maybe some high-order statistics that you see in the data. Perhaps you'll start capturing combination of edges, right? So you can introduce that. So deep belief network has the following structure. You have hidden layers, and then you have restricted Boltzmann machines, the bipartite graph sitting here, undirected graph. And you have something that's called a sigmoid belief network, which is just a bunch of conditional probabilities. And each conditional probability has a sigmoid function. So the probability of this unit taking value 1 really looks at the input from these variables. And so just to specify precisely what the model is, it's a stochastic model. You can specify distribution over all of the variables. You have a restricted Boltzmann machine, which is again a bipartite undirected graph, and you have these conditional probabilities, which is just basically conditional probabilities given by sigmoids. Okay, if you look at this model, the entire model is a mess. If you wanted to do inference in this model, proper inference, it would be very hard, right? Because if I want to say what's the probability that this unit takes value 1 conditioned on the input, if I want to do inference, this, just because of explaining away, you have to condition on everything here to infer, and it's very hard. It's very hard to do. So why this particular model? And so in this case, again, just to pictorially visualize, you have some distribution over H1 and H3. In this case, a 3-layer model, and then you have a bunch of these conditionals. For this particular model, there is also something that's called approximate inference network. And in fact, for a lot of different models today in this space, if you look at variational autoencoders, Helmholtz machines, they all have the generative model and they all have inference model. And you can think of an inference model as some neural network model that infers the parameters or that infers the hidden states given the input. So you can think of it as an approximation to the posterior. Right. Given the data, what's the state of the latent variables? There's some approximation, some recognition model that tries to approximate the distribution over all of these random variables. Now, there is a training algorithm for training these models. So how does it go? You first learn an RBM with an input layer V and H. So you can train this model. There's contrastive divergence, some approximations. So let's say you can train it. Then what you can do is you can treat inferred values from this conditional probability as the data for training the second level RBM. Okay? So what happens here, it turns out that if I tie these parameters, W1, W1 transpose, And if I make sure that V here, let's say it's whatever the size of this layer is the same as this layer, then it turns out that this model has exactly the same distribution as this model. So the distribution of the input here, these two models are basically equivalent. Okay? And the reason why, the intuition why is, just intuitively, if you think about how do you sample data from this model, you're just running a Markov chain up to infinity and you're generating it, right? If I have this model sort of upside down, if I run this up to infinity and do one more step, I will generate the exact same distribution, right? And mathematically, you can just show two models are equivalent. So that's the construction. Now, let's say if two models are equivalent, what you can do is you can say, well, what I'm going to do is I'm going to freeze these parameters, and I'm going to learn this model. Right? So I'm going to sample these states and just refit this model. So why does it help? And then you proceed to the next layer. It turns out, and this is sometimes called unsupervised feature learning, it turns out that layer-wise pre-training improves the variational bound with this particular architecture. So what it does is it basically says the following. For any approximating distribution Q, right, and I'll come back to this later in the tutorial, I can write down the log P of V, I can do that, and I can always lower bound it with this expression. This is something that's called variational bound. Right. This inequality becomes equality if this conditional probability equals to exact posterior, if it equals to P of H given V. This is known as a variational bound. This is known as the entropy of the Q distribution, right? So what's happening here, and that was shown by Hinton and Uite and Simon Asindero back in 2006, they basically showed that if I start with this model, and all I'm going to be doing is I'm going to be, so the lower bound becomes tight, yeah. So what I'm going to be doing is I'm going to be training the second level RBM, effectively improving this term here, right? P of H1. So what this is doing is it's basically saying that this now becomes an RBM, and if I can push this guy up, then my variational bound will increase. That is a little bit fuzzy, but what it does show is it basically was shown that if you get samples from your Q distribution, which is your approximation here, and you train the second level RBM, you're basically improving this quantity here. And by improving this quantity here, you're improving on the bound. So this was one of the first algorithms that basically said that by this construction, if you put another layer, you're actually improving the variational bound. If you put another layer, you're improving the variational bound. Now, of course, there are some conditions. You have to start exactly W1 transpose. So the architecture has to be exactly the same. But it did show that by training these models in steps, you're actually optimizing the bound and the log likelihood, which is something that in the variational inference community people sort of accept as a way of training models. And that was kind of interesting because a lot of people, when they looked at this, they said, well, this is no longer just a hack. It's not like we're just sticking things together, but this actually does something reasonable. There is an objective function that you're optimizing by introducing multiple layers for that specific model. And later on, there was a nice paper coming from Stanford, from Andrew Ng's group, where they basically used convolutional extensions of these deep belief networks. And they've shown that they were visualizing, the first layer was learning these little edges. The second layer started picking up parts. The higher level started picking up faces. So at least some version of visualization of these systems. And if they've trained on faces, cars, elephants, chairs, and they started visualizing what these systems are doing. Yes?
That visualization was what, the most likely?
Yeah, that was the most likely. So they basically looked at particular neuron and they took the most kind of likely activation of the input to see for the firing of that particular neuron. And so they sort of found that there is some kind of, not quite, but to some extent, the notion of part-based. Parts get composed into groups of parts. So when they train on multiple classes, They found class-specific parts, they found groups of parts, and such. So that gave a little bit of inspiration for these kinds of models. And if you look at the convolutional neural networks, it does typically happen that you sort of do find these kinds of structures as well. So I think it's 12 o'clock, so let me stop here and we'll continue. But one message that I want to emphasize again from this talk is that if you look back at the original paper on deep belief networks, the justification for the variational inference, for training these multiple layers, was, I think, is an interesting one, and it gave rise to a lot of people looking into these models, thinking that it's not just something that you put together that works, but there is a very nice theoretical justification as to why adding additional layers is actually solving an optimization problem, right? So you're pushing on the variational bound. Thank you. Yeah, Jim DiCarlo.
Oh, DiCarlo.
DiCarlo.
No.